Just to finish off our differential equations, just looking at some examples in the real world. We have a tank with 30 litres of solutions of a particular chemical in water. The concentration of the chemical is then reduced by running pure water into the tank, and we're pouring it in a rate of 1 litre per minute. So the solution will then run out of the tank at 2 litres per minute, and at any point in time the tank contains X litres of chemical after the dilution starts. We have to show that the rate of change of chemical, number of litres of chemical, with respect to time is this expression here. So what do we know? We know that every minute the volume of the tank is going to reduce by 1 litre, because 1 litre is going in, 2 litres going out. So therefore in T minutes the volume will be reduced by 30 minus T litres. Now, at time T, the fraction of solution in there, we said at any point in time there's X litres, and we just worked out the volume at any point in time is 30 minus T. So the fraction must be there, X over 30 minus T. So we know that. We also know it's escaping at 2 litres per minute, so therefore the rate of flow must be negative 2x on 30 minus t. Negative because it's decreasing, and 2 because 2 litres are going out every minute, so we get minus 2x on 30 minus t. That explains where that expression comes from. So now they want us to use it. Find the fraction of the original chemical still in the tank after 20 minutes. Right? So the original volume, we don't know what it is, I'm just going to call it V. We just worked out dx to t is equal to that, or if we didn't work it out, they gave it to us anyway, so we can keep going on with the question. Separate out the variables. So at time 0, just what we've called V, we want to find that link between x and t, so we can use that formula to find our answer. So integrating that, integrate the dx on 2x, we get a half of log x, and on the other side I have the log of 30 minus t. So the log of x on v is equal to 2 log 30 minus t over 30. Wow. If I pull the 2 into the log, then I've got log equals log, so those things must be equal. X on v is equal to 30 minus t squared over 900. I have an expression for x. When t equals 20, we get v on 9. There's our fraction, 1/9. As I say, I don't know why I didn't do that with just t equaling 20. That would have been quicker. Our logistic equation that we saw yesterday. Population of foxes on an island modelled by our logistic equation there, y, 1 minus y. T equals 0, the population of foxes is estimated to be 1/4 of the island's carrying capacity. Now, carrying capacity is basically the maximum population that the environment can handle. So how much it can carry. It would be the horizontal asymptote. Remember the shape of that logistic curve? Basically it's that horizontal asymptote. Use the substitution y equals 1 on 1 minus w to actually change this logistic equation to something much simpler, and something hopefully we recognise to be that basic growth and decay equation we saw before. So if y is 1 on 1 minus w, then dy to t, well, can't differentiate this with respect to t, but I can with respect to w, but they multiply by the w dt. Now, dy dt is equal to y 1 minus y. Okay, let's transform this equation now. Dy to t, just worked out, is this expression over here. 1 on 1 minus w squared times the w dt. On the right hand side, y 1 minus y, I just substitute in for y. Now, hopefully we can play around with this and get the expression that we want. And sure enough we do. Because if I multiply both sides now by 1 minus w squared, and inside the parentheses there, that algebraic fraction becomes minus w on 1 minus w, and we get some cancelling happening there, and we're left with minus w. So we have our very basic growth and decay equation. Now that allows us to solve this problem a lot quicker, because using the solution, the w dt equals minus w, find the solution of the logistic equation. The initial conditions, they told me when t equals 0, y equals 1/4, but now I need to know what w is. So at that point, w would be -3. Because that's our basic growth and decay question, we know the solution to it straight away. Now if we see this one's dw, but basically if we see dp to t equals minus constant times p, we know the solution is a, some constant, e to the kt, where a is the initial population. So we know the solution to this will be minus 3 e to the minus t. Now, y then, remember we defined y 1 on 1 minus w. And now I just substitute into that, and there's the answer. And you'll see it is in that form we saw yesterday that it ends up in. But a heck of a lot quicker by doing it that way. How long will it take the fox population to reach 3/4 of the carrying capacity? So we want to know when it's 3/4 is equal to that. So y is 3/4. And it's just a matter of solving our exponential equation there. We get log 9, which is about 2.19722. It's about 2.2 years. This one's also a logistic equation, but played around with it a little bit, added an extra factor into it. So we have a rumour. We love our rumours. Rumour is spreading amongst 1,000. Now, okay, our school's a bit more than 1,000, but it makes the numbers nice. 1,000 students in a school at a rate proportional to those that have heard it and those that have not heard it. As time progresses, people care less about the rumour. So the proportion rate is not constant. And that's why it's not just k times that, it's k over t plus 1. It's being divided by time. It's inversely proportional to time. The longer time goes along, that constant gets smaller and smaller. So we have this new logistic equation. Initially, one student starts spreading the rumour, because it all starts with one student, or one person when you're spreading rumours. After 1 hour, 50 students have already heard the rumour. How many students have heard the rumour after 3 hours? So there's our differential equation. I can separate the variables. Now at t equals 0, only one person knows the rumour. That's the person that's going to spread it, because they're the only one that knows it. So when t equals 0, the number of people that know the rumour is 1. We were told after 1 hour, 50 people know the rumour. This is what we have to solve. Well, on the left-hand side, we've got our partial fractions we could do, and we'd end up with 1 on x plus 1 on 1,000 minus x. The right-hand side is just a log function. Subbing into the right-hand side, I get 1,000k log 2, and tidying up our integral over here, there's going to be a couple of log functions, but using the log laws, we can combine that in. We'd end up with the log of x on 1,000 minus x. When I sub in to this, I'll get the log of 1/19 times 999 on 1. There's k, because we want to find now how many after 3 hours. Notice I've left it as k. I'm not going to put that number in. It just will make it setting out hard. So I'll just leave it as k. I can always substitute that in later, but I know what k is. Let's do the integration again. No surprisings, we get the same answer because we're doing the same integrals. But now I know that the log of 999 1,000 minus x, which is the left-hand side, will equal, I'm just saying, some constant number here, rather than having to write it all down. And then over here, I'll just work out what is that constant number. And that constant number turns out to be 1,000 times the log of 999 on 19, 1,000 log 2 times log 4, 2 log 999 on 19. Well, again, I'm not going to write that all down. I'm just going to say, well, that's e to the power of c, but at least we now know what c is. We can sub that in later. Now, we're trying to find x, remember. They're playing around with it. X is equal to 1,000 e to the power of c over 999 plus e to the c. Now I can substitute that c into my calculator and we'll work it out. We get 734.558. So after 3 hours, about 734 students have heard the rumour. In just 3 hours. Lessons we learned there is, don't spread rumours. Okay. So 13e, just more applications of differential equations to look at there.